So first talk, we're excited to have Chris Taylor to join us for the first part of the talk of the session. So we have Chris, who obtained his PhD in theoretical chemistry from the University of Bristol in 2014 and has worked in the group of Professor Graham Day at the University of Liverpool on a variety of research challenges in the field of organic molecular crystal structure prediction and materials discovery. And the title of his talk today is Large-Scale Crystal Structure Prediction, Learning from 1,000 Molecules and Beyond. So Chris, whenever you're ready, please take it away.
Okay, thank you very much for the introduction and for the opportunity to speak today. I'm very pleased to be able to speak to you all today. Rather unfortunately, I have to introduce myself as formerly working with Professor Graham Day at the University of Southampton, as I have since moved on only a couple of months ago. But I'm proud to be telling you all today about some work that I did not that long ago with Graham. About large-scale crystal structure prediction and how we can apply the methods that Graham's group develops to really push the boundaries in materials discovery. So when I say crystal structure prediction, what do I mean by this? So the fundamental question in crystal structure prediction is, if we are given just the 2D molecular diagram of a molecule, can we predict the molecule's most likely crystalline forms, and I say forms, there can be more than one, as many know, of that molecule and the properties of those crystalline forms? Now, this is important because the crystal structure affects the material's properties, unsurprisingly. So if you have some molecule that you are trying to synthesize a functional material out of, or perhaps the reverse, the inverse design problem, where you want a material with certain targeted properties, and you need to decide on a molecule that will lead to a material that gives you those properties, then you need an understanding of the crystal structure. And so being able to predict the crystal structure a priori computationally is an extremely powerful technique. So what does crystal structure prediction, or CSP, actually entail? Well, the sort of fundamental element of knowledge in CSP is this concept of the crystal energy landscape. So the potential energy surface that is defined by the crystalline degrees of freedom, the molecular positions and orientations in the unit cell, and the lattice parameters that describe the shape and size of the unit cell. So if you can predict the shape and size of the unit cell and predict the molecule's positions and orientations within them, then you have the crystal structure. But this is actually quite a difficult problem that requires large-scale computation. It's difficult for two reasons. One is that there is a sampling component to this problem. In even the simplest cases, you have at least 12 degrees of freedom, 3 lattice parameters, 3 lattice angles, the x, y, z position of the molecule, and its orientational angles. So you have at least a 12-dimensional hypersurface that you need to try and sample, and this, in practice, winds up with us having to generate tens of thousands, hundreds of thousands, sometimes millions of unique crystal structures to be confident that we have converged our search and explored the landscape thoroughly. Then the other side of the problem is this is also an optimization problem. Especially in molecular crystals, you have a complex balance of intermolecular interactions holding the crystal structure together, and so you need an energy model that describes those well, and an optimization method that is fast and efficient, because, as I say, we have hundreds of thousands or millions of structures we have to consider. And this isn't just a global optimization problem, as mentioned before. Many molecules are polymorphic. They can exhibit multiple different crystal structures depending on crystallization conditions, and so we care about finding as many of the local minima as we can on the landscape, and certainly the lower energy local minima, and ranking them accordingly. And that's what you see here in the bottom right, is a plot of a CSP landscape where we have the various different hypothetical structures ranked by lattice energy. And one of the things that we typically consider when we are benchmarking or assessing the reliability of our CSP workflow is we look at if there are known crystal structures experimentally of a molecule, then we look at where they lie on our CSP landscape, because one of the assumptions that we make is that the crystal structures that are observed should be among the lowest, if not the lowest energy structures on our landscape. And so if the global minimum is an observed crystal structure, we take that to qualitatively suggest that our CSP workflow is doing the right thing. So having said this, doing CSP for small rigid molecules is now routine. They're very amenable to large-scale automated workflows because you have little to no conformational flexibility to sample, and also if the molecules are small and rigid, then there's limited impact of the crystal packing on the conformation, so the molecular unit really can be considered as constant. And this is helpful because if we want to be able to perform high throughput screening of materials candidates, or candidate molecules for forming materials, then we need to know the performance of our CSP methods on a large and diverse array of molecules, because we want to know that we can explore chemical space and crystal packing space with it in general. And when we say performance, this is talking about both the energy ranking and the geometric agreement with known forms. And we also want to know whether the knowledge that we get out of our CSP workflows are transferable. For example, can we apply AI or machine learning techniques to the data that we get in a way that is then generalizable and transferable to other systems? So for this work, we started off by saying, okay, well, if we think about these very simple tractable systems for us, let's look in the Cambridge Structural Database, limit ourselves to very common element types, low molecular weights, and say molecules are not allowed to have rotatable bonds. We'll use this as a proxy for flexibility, although I'll come back to this in a moment. And how many different molecules are there that satisfy these criteria? And of course, we started this work 2 or 3 years ago now, so this number has only gone up since, but we got over 1,000 unique molecules that satisfy these criteria. And we said, right, let's do CSP on all of them. So what does that actually entail? So in this case, what it meant was that for every one of these experimentally known structures, we extract the molecular geometry and then we gas phase optimize it using DFT method of choice. This doesn't particularly introduce bias in these cases because the molecules are so rigid. So this is mainly just so that we have a sort of consistent starting place for all of our different molecules, and so we have charge densities, quantum mechanical charge densities for these. Because once we have our optimized molecules and our charge densities, then we can start our CSP workflow, which involves generating 10,000 structures in the 26 most common space groups for Z'1 crystals. That's crystals that have only one symmetrically unique molecule in the unit cell. 26 space groups may seem like a strange number, but that's because it turns out that the 26 most common space groups in the CSD cover upwards of 99.5% of all observed crystal structures. Once we have generated 10,000 quasi-random packings in each space group, we then optimize these using a quite simple atom-atom energy model where we have distributed atomic multipoles derived from those charge densities to describe the electrostatics, and an empirically fitted force field to describe the dispersion and repulsion terms. And so once we've done that and we've got our crystal energy landscapes with our optimized structures, we then search for the observed structures, the ones that exist in the CSD, on our CSP landscapes. We do this by using the CSD's Python API to find the closest geometric matches to the experimental structure within our CSP landscape. And as I described before, we take the energy gap between our closest match and the global minimum on our landscape as a measure of the quality or the error, if you like, in our CSP search. In that if our CSP workflow is working ideally, then this energy difference should, in general, be very small, ideally zero. And so once we did that, we found, not necessarily surprisingly, but the degree of the success surprised us. Rigid CSP is extremely successful and reliable for these kinds of systems. We find that 41% of all of the observed crystal structures that we were considering are the global minimum on their CSP landscapes. And in fact, if you consider the fact that these are static lattice energies, we're ignoring vibrational effects, and we know that the error associated with ignoring that is around about 2 kilojoules per mole on average, then that actually means that 75% of all the observed crystal structures are competitive with the global minimum. So clearly rigid CSP works extremely well in general for these small, simple molecules. And we can use this data to help us rationalize certain empirical rules in crystal engineering. I won't spend too much time on this because I have some more things that I need to discuss. But there is a crystal engineering or crystallographic sort of rule of thumb called Wallach's rule, which says that spontaneous chiral resolution is rare. In other words, if you have a racemic mixture, a racemic solution of two enantiomers in your crystallization experiment, then it is extremely rare that you expect that two separate enantiopure sets of crystals drop out. You expect a racemic crystal that contains both. And we find that if we look at all the possible crystal structures that you can form, not just the observed one, for chiral molecules, we find that the data supports that you expect that both the lattice energy and the density is improved in general in the racemic forms versus the enantiopure forms. So obviously, as part of this work, we wanted to see, well, okay, we've got all this data. What can we do with it now? How can we apply machine learning and help get things that are generalizable to different systems? So one of the simpler things that we did was to look at training a neural network energy correction to just based on periodic DFT. So can we improve our energy rankings even further? This is just single point energy corrections, no optimization. And indeed we can improve it. This is perhaps not an entirely fair test because we happen to do so well already using our very simple energy model. What is more interesting is that perhaps unsurprisingly, some of the outliers in our data set, the cases where CSP doesn't rank the experimental structure well, are cases where there is some sort of flexibility in the molecule that isn't well described, that you can't describe in terms of isolated rotatable bonds, like, for example, ring buckling. So what you see here is that for this example system that has this quite large ring, that the blue structure is the experimental one. The blue structure is the CSP one, the element colored one is the experimental one, and you can see these don't quite match up, and that's because our optimized molecule is not close enough to the experimentally observed conformation. So what we did is we took our large sets of CSP structures, we perturbed the coordinates slightly, recalculated energies and forces using periodic DFT, and trained a message passing neural network model, a MACE model, on these perturbed CSP structures and their energies to get a total energy model that we could use for re-optimization, at least close to the minimum. And what we found is that this really gives us very significant improvement because it allows some molecular flexibility and some understanding of the forces on the atoms. And so, for example, in this case, we find that when we apply our neural network potential after having trained it on a lot of this CSP data, we get much improved structural agreement and energetic agreement as well. So in the interest of time, I will only gloss over this bit, but as unfortunately I'm no longer working with Graham, but two of his other team members, Dr. Massi Hafizi and a PhD student, Hannah Gittins, are sort of picking up where I left off. Obviously, one of the important things that is missing from this data is molecular flexibility, and in particular, because we said no rotatable bonds, it means we're excluding all sorts of important intermolecular interactions, particularly hydrogen bonds. And so one of the things that I started doing, and that Massi and Hannah are picking up, is CSP using molecules that contain exactly one, rotatable hydrogen bonding group, doing CSP no longer with one static conformation, but using a grid sampling around this rotatable bond, and then the same workflow as before, optimizing using our empirical potential, and then iteratively retraining our MACE model to incorporate greater flexibility and incorporate some understanding of both the impact of the flexibility on the energy and the forces and the importance of hydrogen bonding. And this is ongoing work and is in preparation for publication, so please look out for that. So I will finish there. I will summarize by saying that our CSP, if you consider the over 1,000 molecules that we treated, there are only 6 cases where we didn't find the experimental crystal structures. We talked about that in the Faraday discussion paper that this was published in. In almost all cases, the experimental structures are among the best ranked and are the global minimum within the static lattice energy approximation. The important thing really for us was that this demonstrated that rigid CSP is reliable enough that we can do very large-scale studies to generate a lot of physically plausible data that we can use to train these improved machine learning potentials and models. The dataset is available. It was released as part of the paper, and as I described, it's being expanded. So I'm quite aware that I'm butting up against the time limit, so I will finish there by acknowledging my former boss, Professor Graham Day, and the Day group, Dr. Patrick Butler, who did a lot of the machine learning work in the work that I've presented today, Dr. Massi Hafizi and Hannah Gittins, who are carrying on the work in the flexible molecule case. I'd like to acknowledge my new boss, Professor Charlotte Dean, and the Oxford Protein Informatics group for sparing me an afternoon to come and talk to you today about this work that I did previously. And obviously, in particular, I'd like to thank AIChemy both for funding and giving me the opportunity to speak today. Thanks very much.